Welcome to ECE 441A 541A. This is a course on automatic control. And on the screen you will see announcements and goals. That's the typical way that we will start class. And today we have a complex process in terms of signing up. If you are wanting to add the class, you'll want to sign attachment 1, but make sure you're either in 441 or 541. So there's two different pieces to the puzzle. If you're already enrolled, you may sign attachment 2. And if you're in 441, assign attachment 2 for 441. If you're in 541, sign attachment 2 for 541. Can it get any more confusing? So I shouldn't see too many signatures on attachment 1, and I'm going to pass attachment 2. Don't try to confuse me. So here is attachment 2 for 441 and attachment 2 for 541. So pick your particular sheet, and attachment 1 is if you're wanting to add the class. Right before class, I posted the passport assignment, and that's due Sunday evening. So you almost have a week to finish that. And on that particular assignment, tell me how you want to be referred to in terms of that's what I'm meaning by the nickname and a way to pronounce your name. Go ahead and give me your official name so that I can keep track of who's who, and your email address, a picture, and something that's unique about you. And then for the interesting part, I want you to read an entire book. No. But I want you to read the summaries of each chapter, and there's 8 chapters. Read the summaries to 8 chapters, and then pick one of those summaries that speaks to you at this particular point in time, and tell me a little bit about that. Explain why you selected that particular chapter summary, and it's relative to how we learn. Making it stick is, how do we make information or knowledge stick in our heads? That's the point of the title. And if you do want to read the book, you can. It's available as an ebook through the University of Arizona Library. But what I want you to do for step 4 of your passport is to simply tell me which of those chapters you resonated with in terms of the summary, and explain why that particular summary spoke to you. And it doesn't have to be a 3-page essay. It can be a short paragraph, a couple of sentences, 2 or 3 sentences. That's the passport assignment. And then I want you to also indicate by your signature that you've now looked at the syllabus, wherever that is. Here's the syllabus of the class. Oh, I didn't introduce myself, did I? Sorry. My name's Hal Tharp. I am a faculty member in the Electrical and Computer Engineering Department. This class is automatic control. My office hours right now are set on Wednesdays, Thursdays, and Fridays. The homework assignments will probably be due at the end of the week. That's why we're having those office hours concentrated at the end of the week. And if you are taking the online version, during the work week, I hope to respond to inquiries within 48 hours. That's the idea. If you're on campus, you can see me during office hours or after class. There's a little bit of justification, teaching philosophy, tips for success. The 2 books, I've had some people ask, do they need to purchase the 13th edition? ideally, yes. If you have an older edition, which is probably less expensive, I will try to include the problem statements from the 13th edition in addition to the problems. And so the context or the material in earlier editions of the class are probably fairly consistent with the 13th edition. And having an older edition should be okay. Just be sure that when you do a homework problem, if it says problem 6 in chapter 2, don't use the old edition to use that. Go and look at the actual problem statement from the 13th edition. If you're in 541, there's another book, Feedback Control Theory. It's a more mathematically based book, and you can access that either as this PDF file that I have linked, or you can through the D2L website. It's in the U of A library. You can click the button near the top right corner of our web page in D2L under Library Tools, and you have access to the ebook there. That's if you're taking 541. A lot of information. I'll let you read that. Here's maybe what you're more interested in. We're planning to have 3 exams. They're each worth 20%. There's homework, and that varies as far as what percent it will represent for you. If you're in the 441 class, that's 10% of your grade. If you're in 541, it's 5%, and the other 5% in 541 will be a project. Now, the 541 students have to do all of the homework. It's just it will be weighted at half of the percent of your grade as the 441 students. We will have lab experiments, and those will be on your own time. We don't have a lab section, but there will be 3 labs that essentially follow along with the course and are effectively going to coincide with exams. And it will be helpful that either you perform the exam or the lab, or at least do the pre-labs prior to each exam. And the exam dates are listed. Hopefully those will work out for everyone. And there are a lot of class cancellations. And so we'll make up for those via the labs. Those are on your own time, and you'll need to schedule those, and those will be team-based labs, and more of that will be forthcoming as we get closer. But you can see that the first one is on system identification and modeling. The second one is on system performance, and the other one is now designing controllers. And that's our 3 labs. Then if you're interested in the final exam, here it is. Everybody always wants to know, is it on the exam? Will this be on the final? Well, here's the final exam. The final will maybe be 15 problems, so maybe I'll not cover 2 of these, but if you can go inside and out, forward and backward with these 17 course outcomes or course objectives, you should be in good shape for the final exam. And you can see that I've identified which of these 17 are associated with the content relative to the 3 exams, and which one is for after the final. And that is then related to the textbook in the last page, I think page 6 of the syllabus, and we're moving quite linearly through the textbook. In terms of starting with chapter 1, you'll want to read that tonight, and then be good to go on Wednesday. Make sure you've had plenty of sleep before you start reading, right? Question? 541, if you're in the class, sign up attachment 2. If you want to add the class and you're a graduate student, sign attachment 1 for 541. If you're in 441, you don't have to touch the 541 sheet that's going around, but make sure you sign in. I don't want to administratively drop you since we're packed in here like sardines. with respect to the number of students. But maybe some will fade away after a week or so. Are there other questions concerning the syllabus, the passport, the structure, what to anticipate in the class? Take my glasses off so I can't see if there's any questions. Homework number 1. I wish we had it, but it hasn't yet been created, but this is just to give you a way to anticipate. It's a few days off, but you can start planning your time schedule appropriately. There is a prerequisite quiz, and this prerequisite quiz helps me gauge where you are as a class, and it may help you understand what I'm expecting from you in terms of where we're starting. Some of it maybe you won't have seen before. That's okay. Just do your best. But do it by yourself. I don't want you in mass giving the same answers. I want to see on average what the class looks like relative to the prerequisite quiz. The class, I will start collecting all of that information in units or modules on the D2L website, and I believe I've located the prerequisite quiz link under Unit 0. That's sort of the preliminary unit of the class. Or you can go to the quiz tab and find that quiz hopefully there. And it's 7 questions. It shouldn't take you that long to answer, but it's multiple choice. So I guess you get a little bit of a head start that way. But one of the questions, it's really difficult. It's which calculator are you going to be using? You can't miss that one. Okay, so you just fill in or bubble sort which calculator you have access to, and that gives me a feel for what you have access to. But we will be using MATLAB throughout the class in terms of a computational engine. The syllabus, if you didn't read all of that as I was scrolling through it, maybe you're quick at reading. If you need a little bit more time, you can find that in a couple of places on the contents page of the D2L website, and that's where most everything will be located on the contents page. Those are the preliminaries. Let's now get into an overview of the course. How many have heard of a concept map? Oh, I guess I should put my eyes on, huh? I didn't see too many hands go up, but I want to give you a very rough picture or concept map of what this course looks like. It's called automatic control, and we've effectively, that's the collective we, it's probably me, I've split it into 3 different pieces, or 3 different parts. The first part is where we start. So this automatic control is going to start with, or begins with, modeling. And that's sort of section 1. Once we are comfortable modeling systems, getting a transfer function, getting differential equations, we've now modeled the system. Now we want to perform some analysis on that system. Is the system stable? Is it moving the way that we want? Is it behaving the way that we want? That's the second piece of the class. Then if it's not working the way we want, or maybe there's a large steady state error, maybe there's something going on that we're not comfortable with, then we want to move into the third phase, which is the design phase of controllers. and that's the third part. And what I want to do now is just very quickly talk about those three parts of the overall class. But that's a very high-level view of what we will be doing. We'll be modeling. Hopefully you remember your physics. You remember how to model mass spring damper systems. Our systems could be from many different domains. It could be electrical, it could be mechanical, it could be electromechanical. Once we say electromechanical, then we have all sorts of things. We could have robots, we could have cars. We are trying to be able to control all of those in this class. If we have a model, then we can analyze it and design our controllers. Let's now talk about this modeling aspect. What are some methods? And I will simply break this down. We're really trying to find a representation of this physical entity that we are trying to better understand or control. One is through physics. And the reason why we are here is because we're really close to physics. No. But this room is pretty close to the physics building, so maybe we'll get a little bit of that information or that vibe, and you'll be better at doing your physics problems. Do you remember anything from physics? F equal ma, we will use that to build our understanding of how we describe systems. How do these interconnected masses, how are they one coupled, and how do we describe that in equations that we can now extract a model from? I'm assuming many of you are from electrical and computer engineering, and so you know your favorite friend, right? Eli the Iceman. V is equal to L di dt, that's physics, but this is now Eli in the form of the voltage or electromotive force, the inductance L, and the time rate of change of current, which is I, and that's the time domain relationship connecting current and voltage of an inductor. And we will do that same thing. That's what we're doing with physics. We're connecting how does this mass move relative to the forces applied, how is its acceleration impacted. That's F equal ma. In the second case, we have ice. I just like putting that into every class that I teach so that I always have some ice. It's kind of warm still in August, and Eli is always in need of some ice. So Eli the Iceman gives you that mnemonic for understanding how do you now model systems that have these energy storage elements in them or as a part of them. That's one way of modeling systems. A second way is more experimentally based. And you could say that this is now doing system identification. Maybe we don't quite know how to model it with paper and pencil, but maybe we can take some measurements. And for that purpose, we might go into the lab and excite the system or kick the system. I'm breaking things, breaking my foot, breaking the cabinet, but we'll be shaking things in this class or moving. And what's that going to do? That's going to excite the system into some response, where this is the output, maybe that's the position of this mass, versus time. And once we have that information gathered, or that particular behavior identified, we will be able to extract from that useful pieces of information. One is you can find its steady state value. That's what this red dashed line is supposed to be referring to. We could find when it peaks, let's say the time to peak, or the peak time. That might be a useful piece of information. We might be able to, with this information between the value it possessed when it was at its maximum and what value of the output it is when it's at steady state, from that we can now find the percent overshoot, and that will give us information into the damping behavior of that system, or how much natural damping exists in that system. We could also go out here, and if we go far enough, maybe this wiggling, maybe it never stops, but it will probably eventually get into a tube, maybe a 1% tube or a 2% tube around this final value. And when we refer then to settling time, we are saying, when did it finally get into maybe this 2% tube around the final value? When did it first go in there and not exit? Obviously, it goes into that green area quite quickly, but it exits that. We're interested in, when does it get into the tube and stay in the tube for the first time, and that's now our settling time, or T sub S. With that amount of information, we will actually be able to identify the system, which I might just abbreviate as system ID, or that now might allow us to obtain a transfer function that models the system from experimental measurements, from data. And we didn't have to go in and do the equations of motion or find its dynamics analytically through physics with Eli and ice or with F equal ma. Now we kick the system, we observe what it does, we obviously know the magnitude of that kick, and then we watch how the system responds. And that will then allow us to find this transfer function. That's in the time domain. We could also do system identification in the frequency domain. For example, you might go into the lab and measure the frequency response of that system, where this is now the magnitude in dB of the system's transfer function. And now we can see that, oh, this frequency response is actually bending or kinking or changing slope at particular locations in frequency omega. Meaning we might be able to identify, oh, the slope is now changed at omega naught. The slope has changed at omega 1. And from that information, do you remember what omega 1 and omega 0 might represent in terms of system properties or system characteristics? What would give rise to this behavior at omega sub 0? What particular system property? Any brave souls on an August morning? What do we have with respect to a transfer function? Just pick a transfer function and just write it down on paper. And what do you see? There's some numbers, there's some different factors, aren't there? There's factors in the numerator, there's factors in the denominator, Those might have particular descriptions. Poles and zeros. Yay! Which is which? Where are your poles? In the denominator. They're downstairs, and when those factors go to 0, your whole transfer function goes to infinity. That's why it's called a pole. Remember, we were scaling poles, or we might scale poles in this class. Circus tents, poles, remember? Everybody been working out this summer? And then we had thumbtacks, which were the zeros. That's where we stuck the rubber sheet down, and those are the factors, or those are the values of S, the frequency values that cause the numerator factors to vanish. Those are zeros. And we have some overall gain. This is now telling us how the gain of that system moves or changes with frequency of excitation. Meaning if I put in a frequency, and now I have to remember that I'm actually communicating with people that can't see me pointing when I point to the white or to the screen, but if I identified a frequency below omega naught, let's say that ended up being 26 hertz. Maybe it's probably going to be in radians per second, so let me just say it's 26 radians per second. How's that? Below omega naught. If I lose my voice, we're done, okay? Class will be dismissed. I haven't yelled at people for a summer, so my voice, I didn't do voice lessons over the summer. I should have. I apologize for that. That was terrible if you're listening, wasn't it? Where were we? 26 radians per second. We go and we move up and we find that maybe our magnitude is 10 dB at that frequency. Then we move over to omega 0 and something happens. What happened at omega 0? You have a pole. And depending on the slope change, if it's 20 dB per decade, if it's flat before omega naught, and if it's 20 dB per decade, we know we had one pole at omega naught. And then it obviously is breaking or kinking down again at omega naught, or at omega 1. These two can be referred to as break frequencies, but knowing that, now we can say, oh, we have a factor, and one of those factors has a pole at omega naught. The other factor, we have another pole at omega 1. What's the order of my system? Second order. And based on what the magnitude is at low frequencies, I now have the gain of the system, and I now have a model. I have a G of S. You've done that with via inspection of your frequency response or of your Bode plot, experimentally. And you could go into the lab and excite your system with a given frequency, and it will reach a steady state, and that steady state now tells you what the magnitude and phase is at that frequency. And if you did that for an infinite amount of frequencies, you could reconstruct this magnitude plot. And that's what your machines do when you push a button and say, give me the frequency response of this system. It effectively does that. It excites the system and looks at it, and then it gives you that magnitude and phase information. That's the first piece of our class, the modeling piece. We can do the modeling analytically with physics. We could do the modeling experimentally. In the lab, first lab, we will identify the system experimentally. Don't go in and kick the lab, but you'll be able to push the button, and that will shake the lab. And it will start shaking. And if it starts going, hit the abort button. There's a stop button or an abort button. I want you to push that. I don't want you damaging the machine too much. It just lowers your grade 20% if you make it rattle. That was a joke. But take it to heart that you do want to hit the button if it starts misbehaving. It'd be nice if every time something misbehaved, we could just push a button, wouldn't it? That's available to us in the lab. Some other venues that may not be available. The second part of the class is our analysis piece. Just like in modeling, we looked at two different domains. We need to be very comfortable working in both domains, the time domain and the frequency domain. And sometimes I'll move over and I'll say we're in the time domain. I can't see, so you guys don't have to get too nervous, but I'll hopefully not trip getting over to the other side. And then we'll come over here and we'll be in the frequency domain. We can do analysis the same way. We have time domain analysis and frequency domain analysis. We've already looked a little bit at what happens in the time domain, and you'll get very comfortable with this second order system behavior. And in the time domain, we can be playing with differential equations. And that will allow us then to identify particular properties. What was T sub P? T for time, P for peak. That was the peak time. This might be Y sub P, the value of the output at that peak time. This particular value might be the steady state value of the output Y, and when we get to that steady state, maybe we are now into the 2% tube. Now that's our settling time, which we will then use or know that that's now 5 tau. That's actually the 1% settling time. Maybe I should put that. The 2% settling time, and these are just approximations, is 4 tau, 4 time constants. Obviously, a 1% tube is further out in time than the 2% tube. Thank you. If you didn't have a chance to sign in, please do after class catch me. We may have to exit quickly. I don't know if there's another class after us. So far, there's not a class before us, which gives me enough time to sort of set up, which is good. Here to identify these terms again, this was the peak time. T sub S was the settling time. And something that we will use quite a bit is the PO, the purchase order. Oh, I'm sorry. The percent overshoot. You guys haven't, well, maybe you have started worrying about purchasing, but that's not what that PO stands for. This is percent overshoot in this class. In the frequency domain part of our analysis, now we might have transfer functions that we're playing with. From 320, you better be experts at Bode plots. If you're not, become experts. We also are going to be working with pole zero patterns in the S-plane. This is the complex S-plane. This is the real part of S, and this is the imaginary part of S, and we will now be gaining insight into a system's behavior based on where the poles and zeros are located in this complex S-plane. Maybe our system has 3 poles, and the poles we will represent with X's. Zeros will be open circles. Here I haven't indicated any zeros. We will start to learn how if we put this system into a closed loop, we fed back the output and cranked up the gain, we will start to understand what the system will do via a root locus. How do the roots migrate as we adjust the gain k? And we will find that the roots behave something like that. And in the closed loop, let's say that our closed loop poles we're now where we've cranked up the gain to put the closed loop poles at those triangle locations. Is that a good thing? Yes, no. What we are trying to do is make sure that we stay out of the right half plane. The right half plane, which is the right half of the complex plane, has real parts that are positive, and that looks like e to the t, e to the 6t. Those exponents are positive, and those are going to go unbounded with time. This would not be a good design. So we might have to introduce a controller to try to pull those poles or those red root locus branches back into the complex left half plane and guarantee stability for that particular system. And that's what the third part of the course is going to be about. Controller design. Now we get to play with block diagrams. Well, we'll start playing with block diagrams before we get to controllers, but here might be our plant. I might say plant, and that's not some green leafy thing. That's now our system. I had a student, and she said her dad was reading her master's thesis, and he goes, I don't understand. I thought you were an electrical and computer engineer, and all your thesis is talking about are plants. She goes, Dad, a plant is a system, not a green leafy thing. So this is a system, but we will probably, traditionally, we'll just call it a plant. And we might like the way that plant behaves, we may not. If we don't, then we will want to manipulate or change the behavior of that system by introducing a controller which has its own transfer function, which we will call D of S. And we may not want to look at this in an open loop fashion. We may actually want to measure the output, Y of S, feed that back, compare that with the reference input that we've introduced, R of S, and hopefully then the closed loop system that we end up with will behave in a manner that we're more comfortable with or that we prefer. The third part of the class then is figuring out how do we design this capital D of S transfer function. What does that look like? And we'll have many different ways of designing that capital D of S. We might do it using a root locus approach. We might use it or design using Bode plots. We might design using state space equations. We have at least 3 different areas that we could start thinking about or examining in terms of designing controllers. One of the first controllers that we will look at is fairly basic. It now has a gain, it has a zero factor, and a pole factor. What order is that controller? That's a first order. And we'll do that via using Bode plots. We'll design first order controllers. We may, in the state space, do full state feedback design, and that's a little different beast. So it gets its own circle in this concept map. But we won't want to just restrict our attention to first order controllers. We may want to go to higher order controllers, and one of the first higher order controllers might be PID. No, don't say PID. If you are interviewing or going out somewhere, it's PID. You don't read it. You don't say PID. Oh, I have a PID control. No, I have a PID controller. It's a proportional integral derivative. It's kind of related to ice and Eli, isn't it? But there we were saying Eli and ice. Now don't call this PID. Call it PID for proportional, integral, and derivative. We have three different pieces, and so this now naturally leads into a second order controller, and we may have to even go higher and design third order controllers, but we can do that in the Bode plot domain or the root locus domain, and we're obviously doing that when we start doing any kind of observer design in the full state setting. And what is all of this helping us do? It's helping us try to modify or change the dynamic behavior of our system. If we now had a system like I said, you're going to get very comfortable drawing this diagram or that response. Maybe that's our open loop response. Let me label this open loop. This is in the time domain. Maybe we don't really like that because, in fact, our boss wanted that, maybe the mass, maybe this is the trajectory of the mass, and we were trying to move that mass, and our boss wanted us to get to a steady state indicated by that blue line. And you show him the plot, and he immediately goes, or she goes, your boss, goes all the way out here, and they go, wait a minute. I don't like that steady state error. That's huge. Can't you do better than that? Who is your control instructor? You go, oh, I understand. I'll go back and redesign a controller or improve. This is just the open loop. So now you say, let me design a closed loop system. Let me introduce a controller D of S to try to make, before what we were doing, oh, I'm putting my hand over the controller. Did you catch that? So if you simply erased D of S and introduced a signal, boy, this is maybe your input, and I'm in the frequency domain, so that's a pet peeve of mine. Don't label that U of S or U of T. This is now U of S. Maybe you don't have anything other than an input signal U and an output Y, and that's what gives rise to this open loop behavior. But now you realize that maybe I need to reduce the steady state error. I want to make E steady state smaller. I want that final value of my response to get closer to my target or to my reference input. And you might then, with a control design, what color I'm running out, you might be able to design a controller that has this behavior, where now this green line is our closed loop response. And now what's the steady state error? Maybe it's 0. Maybe you've introduced an integrator. That's part of that PID. You now have an integrator term, and that's integrating out that error signal. It's trying to minimize that error to zero. You learned about integration in calculus. Now you get to use it as a tool. You get to build an integrator in your controller, and boy, those integrals are powerful, but they also deteriorate your transient behavior. So there's a trade-off. There's always a trade-off in control. Steady state accuracy versus transient behavior. But here we're getting a pretty good transient response. It gets to our final value quicker, and we have zero steady state error. And maybe we could do that with just a PID controller. This result then is the impact of our controller, which is this D of S, on the transient response. Now, I made such a big deal about PID. What does PID look like, maybe, in terms of a transfer function? It had a proportional piece, and you'll be designing a PID controller in the third lab of this class. Maybe you just say, I want a proportional controller. You just want the P in PID. Now your controller is just a gain, and you can adjust that gain. So I'll be adjusting knobs a lot in this class, and so will you. With a PID controller, you now have the ability to adjust 3 knobs independently. You now have an integrator. What's that look like in the frequency domain? Well, an integration in the frequency domain is 1 over S. And now we have a gain, K sub I, associated with it. We now have a PI. We could have a PI controller. We wouldn't maybe not need the derivative controller. But this now, a PI controller, is good at adjusting steady state accuracy. The derivative part is now, what's a derivative? You're thinking slopes. It's anticipating where you're going or what you're doing. So the derivative term is helping you sort of predict what might be happening in the future, and that gives you better transient behavior qualities in your controller. And in terms of a piece, it's now K sub D over S. Now, you don't want to introduce a pure derivative, and so practically you would probably put this over some really fast pole where P is really big. But effectively, you now have this PID controller. And now you can start using your calculus. You can do differentiation, derivatives, integrals. It's just taken you 3 years to get here, right, with respect to your calculus. Or if you did the AP calculus in 8th grade, it's been a few years maybe. You got your 5 as a freshman in high school on your AP exam. Didn't even have to take differential equations here. I was talking to a freshman Friday, and he's already beyond differential equations. I go, good job. Way to go. Any questions on what we've talked about this morning? Again, that clock is fast, so I'm releasing you early. Yes?
Why do you want to use a pure derivative?
The reason why we don't want to introduce a pure derivative is if you think about what might happen if there was noise in your system and the derivative is now amplifying that noise, that could really swamp everything. And for that reason, you might want to roll off that amplification effect of that derivative at high frequencies. And that's why that S plus P term is in the denominator of that derivative in a practical setting. I'll see you on Wednesday.